All right, today we're going to talk about using Lhopitals Rule in order to evaluate limits that are of the type 0 over 0 or infinity over infinity. This is going to be our first example. And the key here is to not get too happy with using Lhopitals Rule. You can only use Lhopitals Rule in certain situations. It's not a rule you can use on all limit problems, so you have to be careful. And the first thing I want to caution you is to make sure that before you apply Lhopitals Rule that it meets the conditions for being an indeterminate form. All right, and the idea of Lhopitals Rule basically says if you want to find the limit, then all you really need to do is take the limit of the top, the derivative of the top, divided by the derivative of the bottom. So maybe we will write it in this way. The limit as x approaches a, some number, of f of x over g of x is equal to f prime of a divided by f prime of, that is not right, f prime of a divided by g prime of a. All right, so basically pretty simple. Take the derivative of the top divided by the derivative of the bottom. So let's just do this first example. If you plug in 0 here and here, well, you will see that the sign of 0 equals 0 and x is 0. So this fits Lhopitals Rule. Now we know, because of earlier in the year, that the answer is 1, because when we did this earlier in the year, we remember that the sine of x over x is that value, is that graph there, and the key value that there's a hole actually right there, and as x approaches 0 from both sides, the y value approaches 1. And we memorized that earlier in the year, probably the first or second week of school. But now we're going to use Lhopitals Rule and make it a lot easier. So the derivative of sine is cosine, and the derivative of x is 1. And then now when you plug in your limit, you get cosine of 0 over 1, and that is 1. So that is the answer to, well, we'll call that letter A. All right, and then letter B, we will say the limit as x approaches 0 again of the square root of 1 plus x minus 1 over x. All right, so earlier in the year we learned a method for solving these limits, and it was multiplying the top and bottom by the you'd have to rationalize the top and bottom by multiplying by the conjugate of the numerator, which has the square root. All right, but instead we're going to use Lhopitals Rule, or at least we're going to check to see if we can use Lhopitals Rule. So if we plug in 0 into both of these, we get 1 minus 1 on the top, which is 0 over 0. So we can apply Lhopitals Rule. And if we remember that the square root is the 1/2 power, the derivative is simply going to be 1/2, leave the inside function alone, 1 plus x, drop the power down, and then multiply by the derivative of the inside, which is just 1. And the derivative of -1, the rest of the numerator is 0. And then the derivative of the bottom, which is x, is just 1. So essentially we have 1 over 2 square root of 1 plus x. And then when we plug in 0, we end up getting 1/2 as our limit. All right, part C is one of those problems where you have to be careful, because from first glance you may think, oh, it's a limit problem, I need to do Lhopitals Rule. But let's just see if Lhopitals Rule even applies here. It says the limit as x approaches 0 from the positive side of the natural log of x over x. Well, let's just first and foremost graph the natural log of x. it's going to look like this. Has an x-intercept of 1, 0. All right, so that is your natural log of x function. And so as x gets closer to 0 from the positive side, the y value is approaching negative infinity. So our numerator is negative infinity. And our denominator, well, think about it, as x approaches 0 from the positive side, x is going to be a really small number. So the denominator is going to be a small number. Okay, is this 0 over 0? No. Is this infinity over infinity? Absolutely not. So this is just a basic limit problem. No real method here. You just have to look at it and say, okay, if I have a really, really big number on the top divided by a really, really small number on the bottom, that's going to make the overall number even bigger. To give an example, if I have 4 over 1/3, all right, 1/3 is a fraction, but you're flipping 1/3 and multiplying, it's going to be 12. The smaller the fraction, the bigger the overall number is going to be, and this is a negative numerator, so the limit is simply going to be negative infinity. All right, let's look at letter D. Plugging in infinity on the top, we get infinity, and on the bottom, as x approaches infinity, e to the infinity will simply be infinity, plus 1 is still infinity, and if you look at the natural log curve, the natural log of infinity is going to be infinity as well. So this is an infinity over infinity situation, so we need to use Lhopitals rule. So we're going to take the derivative of the top. The derivative of x is simply 1. And the derivative of the bottom, well, that's a natural log function. And one of the reasons why I do like doing Lhopitals rule at this point of the year is that it does refresh us on all of our derivatives and stuff. So the derivative of natural log is u prime over u. And the u prime would be 2e to the 2x divided by u, which would be 1 plus e to the 2x. All right, and at this point we want to multiply the top and bottom by 1 plus e to the 2x, and so that's going to essentially cancel out the 1 plus e to the 2x on the bottom. And that's going to put it on the top here. So we're going to have 1 plus e to the 2x divided by 2e to the 2x. All right. So now when we plug infinity in, well, there's a couple ways of doing this. One way is to plug infinity in again, and you will still get infinity over infinity. So you could do Lhopitals rule a second time. Or you could break this up into two fractions by using a little bit of algebra. And so the first fraction is going to be, so let's say we'll take this and divide it into both. So the first fraction is going to be 1 over 2e to the 2x. And the second fraction, well, the e to the 2x's are going to cancel, and you're just going to be left with 1 over 2. Now, as you let x approach infinity, you're going to have 1 over infinity plus 1/2. Well, 1 over a really big number is going to be close to 0, so the overall limit is going to be 1/2. All right, now we're going to talk about how to use Lhopitals rule on problems that involve the differences of, let's say, infinity minus infinity or negative infinity plus infinity. Essentially something that appears to be 0 at the beginning, but really may not be 0. All right, so because infinity minus infinity, well, it's only 0 if both of the infinities are the exact same infinity, if that made any sense. But if one is a bigger infinity than the other, well, then clearly it's not 0. So let's see if we can figure out, let's say we have the limit of as x approaches infinity, of the function x squared minus x. All right. Well, we can pretty much see this is going to be infinity. It's not 0 because x squared is a bigger function than x when you're squaring numbers. So the answer is really going to be infinity here. If you want, you can factor out an x, and you'll get x times x minus 1, which ends up being infinity times infinity, which we know is clearly infinity. So that's the answer to that one. The next one is the limit as x approaches infinity. And we have x e to the 1 over x minus x. All right, so from first glance, this looks like the answer should be 0. I mean, you plug infinity in to here, and you get infinity. You plug it in here, you get infinity. So infinity minus infinity must be 0, right? Well, let's just see. We're going to factor out an x, and we're going to end up getting e to the 1 over x minus 1. And what you have to do with a lot of these problems is you have to rewrite it so that it's in the form of 0 over 0. So you just have to use a little bit of algebra to try to rewrite it to get it in the form. So we can actually rewrite this as e to the 1 over x minus 1 over 1 over x. Now let's just make sure that makes sense to you. I want to make sure that you understand that this is the same as this. If I were to multiply top and bottom by x, it would cancel out the x's on the bottom, and it would put the x right back on top. So that is the same thing. So I'm just going to erase that, and we're going to work from here. All right, so let's see if this is really 0 over 0. All right, if I plug infinity in for x, then e to the, well, let's just say 1 over infinity is approximately 0, and so we have e to the 0 minus 1. Well, we know e to the 0 is 1, so 1 minus 1 is 0, and 1 over infinity is also 0, so we have a 0 over 0 limit, so we can use Lhopitals rule. All right, so if we take the derivative of the top function, we remember from the first semester that the derivative of e to the u is simply e to the u times the derivative of u. So this is a chain rule. So this is going to be e to the 1 over x times the derivative of 1 over x, which is negative 1 over x squared. All right, and then on the bottom, we have the derivative of 1 over x, which is nice and convenient, negative 1 over x squared. Hey, that's good because these two are the same. They're going to cancel, and then we're going to be left with the limit as x approaches infinity of e to the 1 over x. And so once again, as x approaches infinity, you have 1 over infinity as your power, as your exponent, and 1 over infinity is approximately 0, and e to the 0 is 1. So that is the limit for this problem. All right, let's do one more of that same type, something that appears to be 0, but it's not really 0. If you plug in 1 into this limit, you have the natural log of 1, which is 0. So you essentially would have 1 over 0 minus 1 over 0. And 1 over 0 we are calling infinity, minus infinity. And so a lot of students will think, hey, that's just 0. But it's not, because those two infinities are not exactly the same value. All right, so we need to figure out what the actual value of this limit is. And so what we're going to do is we're going to combine these fractions by getting a common denominator. So we're going to multiply the first fraction top and bottom by x minus 1. So we're going to have x minus 1 over the natural log of x times x minus 1. And then the second fraction, we're going to multiply top and bottom by the natural log of x. So once again, the denominator is going to be natural log of x, x minus 1. And the numerator is simply going to be natural log of x. All right, so we can combine that into one denominator. So natural log of x, and then x minus 1. And then the top is going to be x minus 1 minus natural log of x. All right, let's see what we get now. All right, now when you plug in 1, you're going to get 1 minus 1, which is 0, minus the natural log of 1, which is 0. That's going to be 0 on the top. And on the bottom, natural log of 1 is 0 times 0, so 0. And so, once again, we may think, oh, the limit is just 0. No, it's not. This enables us to use Lhopitals Rule. So we're going to take the derivative of the top function, and let's see what we get. Derivative of x is simply 1. The derivative of negative 1 is 0. The derivative of negative natural log of x is negative 1 over x. All right, and then on the bottom, we can do the product rule. So we have the first, which is the natural log of x, times the derivative of the second function. Well, the derivative of x minus 1 is just 1, plus the second function, x minus 1, times the derivative of natural log of x, which is simply going to be, let me put this in parentheses, 1 over x. All right, we got a lot of fractions and stuff going around, so I am going to use my knowledge of algebra, and I'm going to multiply top and bottom of this fraction by x. That way we get rid of that denominator. So top, we're going to distribute that, and we end up getting x minus 1. And on the bottom, we're going to distribute this x to here and to here. So that's going to give us x natural log of x. And then the x is going to cancel with the other one, and it's going to be plus x minus 1. So we plug in 0 into our limit, into our function, and, excuse me, not 0, plug in 1, which is the value the x is going towards, and you get 0 over 0 again. Oh man, we didn't get anywhere. So now we need to use Lhopitals Rule a second time, because, hey, anytime you get 0 over 0, you can keep using Lhopitals Rule as many times as you want. So the derivative of x minus 1, once again, is 1. The derivative of the bottom, well, we're going to have to do the product rule again. So the first function is x times the derivative of natural log of x, which is 1 over x, plus the second, which is natural log of x, times the derivative of x, which is 1. The derivative of the x term right here that I'm underlining is just 1. All right, so plus 1. And then the derivative of negative 1 is 0. All right, these are going to cancel, so we end up with 1 over 2 plus natural log of x. Now, when we plug in 1, let's just see what we get. Limit as x approaches 1. Well, natural log of 1 is 0, so our final answer is 1/2. And there's the power of the Lhopitals Rule. All right, in this third set of problems, we're going to talk about how to use Lhopitals Rule on products of the type 0 times plus or minus infinity. And you have kind of been conditioned to think that 0 times any number is 0. That is true if the number is really 0. But we know that these are limits. These are limits. And so a lot of times we're looking at numbers that are approaching 0, but not really equal to 0. All right? And so it's not necessarily going to be 0. Sometimes it will, but a lot of times it will not be. All right? So this first example, we have the limit as x approaches 0 from the positive side of the square root of x and times the natural log of x. Now, you may be wondering, why are they putting this from the positive side? Well, it turns out both of these functions that we're dealing with here do not have a domain less than 0. So there is no x approaches 0 from the negative side, so they're just putting that it's coming from the right side. Okay, so if we plug in 0 here, once again, let's just kind of remember what the natural log of x graph looks like. This graph right here is going to look like that. So as x approaches 0, you have negative infinity. And so we'll just put negative infinity above there. And then as x approaches 0 on the square root curve, well, square root curve just looks like that. Well, you get 0. So 0 times infinity you may think is 0, but let's just hold off. All right? So once again, we want to rewrite this so that it is in the form 0 over 0 or infinity over infinity. So we can say natural log of x divided by 1 over the square root of x. Now once again, make sure that makes sense to you. If you multiply by root x on the top and bottom, the root x will cancel and you will end up with the same thing you started with. So I'm going to erase that, but just want to make sure you understand what we're doing. And now when you plug in 0, you will get negative infinity over infinity. All right, now we can use Lhopitals rule. So we're going to take the derivative of natural log of x, which is 1 over x, and we're going to take the derivative of the bottom fraction, which is going to be, well, let's just see what that's going to be. We can rewrite this to be x to the negative 1/2. So that's going to be negative 1/2 x to the negative 3/2 power. And if we rearrange that a little bit, then that is simply going to be negative x to the 1/2 power over 2. All right. The way I did that was basically multiplying top and bottom by the flip of this fraction, and you can kind of do a little bit of math there. And then now if you plug in 0 into this limit, you do actually get 0. But it's not always going to be that way. All right, let's see if we can squeeze another example here. And let's say we have the limit as x approaches 0 of the cotangent of 6x, and that's going to be times the sine of 2x. All right. Well, if we plug in 0, we're going to get 0 for the sine of 2x, and the other one is going to give us some sort of infinite limit there. All right, and once again, let's explain that. The cotangent is cosine over sine, and so if you plug in 0 into the cosine function, you're going to get 1, and you plug in 0 into the sine function, you're going to get 0, so that's infinity. All right, so let me erase that because I think you guys already know that, but just wanted to show you that there. So this is going to be infinity times 0. All right, so we need to rewrite this so that it looks like this. We're going to leave the sine of 2x on the top, and then we're going to divide by 1 over cotangent of 6x. All right, now 1 over the cotangent is simply tangent. So this is going to be sine of 2x over tangent of 6x. All right, let's see what type of limit we get now. If you plug in 0 into the sine function, you get 0. Plug in 0 into the tangent function, you get 0. Hey, we can use Lhopitals rule. So we're going to use Lhopitals rule, and we're going to take the derivative of sine of 2x, which is going to be cosine of 2x, but don't forget the chain rule. The derivative of 2x is 2, so that goes out in front. And then the derivative of tangent is simply going to be secant squared of 6x, and then the derivative of 6x is 6, so chain rule. And now we're going to plug 0 into our limits, and the cosine of 0 is 1, so our numerator is 2, and the secant of 0 is also 1 times 6 is our denominator, so the fraction becomes 1/3, and that is the real value of this limit. All right, the last type of limit that we want to look at are powers, indeterminate powers of the form 1 to the infinity, or 0 to the 0, or infinity to the 0. And you may think, well, 1 to any powers is 1, right? Well, you got to remember that these are limit problems, so it may not be exactly 1 raised to a power. It could be like 1.00001. And if you raise that to enough powers, the question becomes, is it really still 1 or is it something more? So that's what we want to work on. Now, when you have any of these forms, the best way to do it is to evaluate this by taking the log first. So this was going to be a little complicated, so we're going to try to take it slow here. What we're going to do is we are going to let y equal this function. Well, first of all, before we do that, let's prove that it is indeed a 1 to the infinity problem. Well, as x approaches infinity, the inside of this is simply going to be 1 plus 1 over infinity, which is 1 plus a really small number. So do you see what I'm saying? It's not just exactly 1, it's 1.0 something. And you're raising that to the infinity power. So this is a 1 to infinity type of indeterminate power. So we're going to let y equal this function right there. And so our goal is to find the limit as x approaches infinity of the function y. All right? And so we're going to work on this function, and we're going to take the natural log of both sides. So we're going to say natural log of y is equal to the natural log of 1 plus 1 over x to the x. You're saying, well, why would you do that? Well, because there's a property of logs that we want to take advantage of. We can move this exponent to the front of that log, and so it's going to become natural log of y equals x natural log of 1 plus 1 over x. All right? And so now what we want to do is we want to take the limit as x approaches infinity of both sides. So I should have left room for that. Tell you what, well, you got the point. All right, we want to take the limit as x approaches infinity of both sides. And if we do that on the right side, we can rewrite this as we did earlier in this video. And we're going to rewrite this as the natural log of 1 plus 1 over x over 1 over x. And once again, we are going to be taking the limit as x approaches infinity of that function. And then on the left side, we have the limit as x approaches infinity of the natural log of y. All right, so on the right-hand side, we recognize that we have the natural log of 1, which is 0, over 1 over infinity, which is 0. So we can use Lhopitals rule. We're going to take the derivative, and we are going to get the derivative of natural log is 1 over the stuff. All right, 1 over the stuff. So there's that, times the derivative of the stuff. Well, the derivative of 1 is 0. The derivative of 1 over x is simply negative 1 over x squared. And all of this is divided by the derivative of the bottom, which is negative 1 over x squared. And we're going to see that this negative 1 over x squared is going to cancel out nicely. And that leaves us with 1 over 1 plus 1 over x. All right. And so now, if we take the limit as x approaches infinity of this, which is equal to the limit as x approaches infinity of the natural log of y, well, as x approaches infinity, we just get 1 over 1, because 1 over infinity is 0, so that's just 1. Okay? So this whole limit right here just turns into 1. And you may be thinking, well, that's my answer. But remember, we are ultimately after the limit as x approaches infinity of y, not the limit as x approaches infinity of the natural log of y. So this is what we need to do. We need to do a little clever trick. I'm running out of space here, but we can rewrite y as e to the natural log of y. You're saying, well, how would you know that you need to do that? Well, just experience. All right. So natural log of y has a base of e, and there's a property with logs that when this and this are the same, you simply get y. So we rewrote y as e to the natural log of y. All right. And so now we're going to take the limit of both sides. So actually, I'm going to continue this right here. So the limit as x approaches infinity of y is equal to the limit as x approaches infinity of e, squeezing this in here, to the natural log of y. All right, we have already established that the limit, so let me just focus on this. The limit as x approaches infinity of the natural log of y is 1. So this right here is just 1. So our overall limit as x approaches infinity of y is simply e to the first power, or e. All right, I'm sure that was very confusing to you, so we will answer any questions you have on this or the next one in the notes tomorrow in class.